I want to add to the concept, now we've talked about correlation, and as I've said, we abbreviate that as R. There's another concept that's directly related to the correlation coefficient that's called R squared, and it's not hard to guess what that is. You just take R, your correlation coefficient, your Pearson's correlation coefficient, you square it, and you get a quantity called R squared, and that's going to come up as we talk about linear regression. In this case, if you square 0.78, you get about 60.61, and that R squared has a nice little interpretation. The R squared gives the proportion of variability in the outcome variable that is explained by, I'm putting explained by in quotes because I don't want to imply causality here. It might be better to say something like is accounted for by the predictor or predictors in the model. It's also, when we get to multivariate linear regression, you'll see it's also a model, a measure of model fit. But so you could interpret in this case the R squared is 61%. One of the interpretations of that would be that 61% of the variability in ratings of President Obama can be explained by your political bent. That means 39% is left unexplained. That's represented by the scatter around that line. Just knowing your political bent does not completely tell us what how you're going to feel about Obama. But once you know a person's political bent, you have a pretty good sense of where they're going to fall on the spectrum with regards to Obama. But there's still some unexplained variability. 39% of the variability is unexplained, so there's other things besides your politics that determine whether or not you like President Obama. And I found this little illustration of the R squared on Wikipedia Commons, and I thought it was a really nice illustration, so I'll just walk you through it here. On the left-hand graphic here, what you're seeing is y bar is the mean for y. So this would be the mean of your outcome variable. So this is just like the mean ratings for Obama in my class. On average, if you don't know anything about a person's political bent, well, in my whole class, what was the overall mean feelings about Obama? If you compare an individual student from my data set to the mean, that difference we can call a residual, or that's the difference between that given person and the mean. It's their deviation from the mean. If you square that, that's what that square represents there visually here. If you square that, that's the squared distance from the mean. Well, how did we calculate variance for y? We calculated the variance for y as a function of the squared distances from the mean. So these red boxes here are representing the unexplained variability representing all the variability essentially of different feelings about Obama in my sample. On the right-hand panel here, what you're seeing is, now let's throw in a predictor variable. Now we know something about the students. We know their political bent. And we know that there's a relationship between political bent and feelings about Obama. We can draw that line. Now, if you know a person's political bent, you can say with some error, but not as much error, about what you'd expect their feelings about Obama to be. That's what's represented by the line there. Now you can see that if you compare the distance between an individual person and the line, what we call a regression line here, a best fit line, the distance is much smaller. Once you know a person's political bent, the distance, the scatter around the line, represents the remaining variability in feelings about Obama. And that's represented, those squared distances are represented as blue boxes here. And you can see that most of the variance in Obama, if this was Obama, and of course, if this was the relationship between political bent and Obama, you can see that most of the variability, which is represented by the red boxes, most of that goes away once you know a person's political bent. There's very little unexplained variability left over, which is what's represented by the blue boxes. So this would have a very big R squared. Most of the variability in feelings about Obama is explained by political bent. That's the idea of the R squared, and I think it's just nicely pictured there. Last week we saw an example about chocolate and Nobel Prize winners. So this was looking at the per capita chocolate consumption in a given country and the number of Nobel laureates per population that they produce. And it made this nice interesting graphic where you can see the more chocolate seems to be related to more Nobel laureates. And we talked about this as an example of correlation does not equal causation. But I had shown you in this graphic that the correlation coefficient here was 0.79. It was highly statistically significant. Again, of course, it doesn't mean that if you eat chocolate you're going to be a Nobel Prize winner. Wouldn't that be great if that were so? There's, of course, other variables explaining this relationship. If you square R here, if you square 0.79, you get an R squared of 63%. Again, that would say that 63% of the variability in Nobel Prize laureates in a country would be explained by chocolate consumption. Well, again, you have to be really careful with that language because you don't want to in any way imply causality between those two variables. The chocolate consumption is a marker of something else here. People like to say, to take the correlation coefficient and to try to have a benchmark for what's strong correlation, what's moderate, what's weak. There's various rules of thumb running around out there, and with little consensus, you'll hear different things from different people, but a general guide that you might use is if you're above 0.7, that represents strong correlation. Between 0.3 and 0.7 is moderate correlation. Maybe 0.1 to 0.3 would be very weak correlation. And anything other than that is basically pretty close to zero. That's just one rule of thumb, one guideline. It's just a rule of thumb. And it depends on a lot on the problem at hand. So you maybe have cases where it's important to explain 5% of the variance in an outcome variable. That is a very small correlation coefficient. It could actually be important because maybe it's hard to explain, there's hard to find any predictors of that particular outcome. There may be other cases where a correlation of 0.7 is actually not that good. So it really depends on the problem. But that's just a rough guide telling you about the magnitude of the correlation coefficient. When we're dealing with correlation coefficients, of course, we're also going to want to generate p-values and confidence intervals. We're going to want to make inferences about R. I actually told you about the distribution of R as an example of a statistic in Unit 5. For R, the null hypothesis is that R is equal to 0. 0 means no linear relationship. The alternative would be that it's not equal to 0, which would mean that there's some linear relationship, either positive or negative. I already told you, of course, about the distribution of the correlation coefficient. You may not remember the details of it, so I'll review it here. So it turns out that the correlation coefficient, like all things when we're dealing with means, has a normal distribution for large n and a t-distribution for small n. It's a t-distribution throughout, but as soon as you get on a t-distribution where your n is greater than 100, you might as well call it a normal. The mean of the distribution of a correlation coefficient, of course, is going to be the true correlation in the real world, the true value. The standard error for a correlation coefficient, I told you, was roughly the square root of 1 minus r squared divided by n. I actually cheated just slightly here. I left out just to make things simple. If we want to be really precise, it's really the standard error is the square root of 1 minus r squared divided by n minus 2. Of course, if you're talking about an n of 100 or more, if you subtract 2 or you don't, it's not going to make any real difference in the magnitude there. But if you want to be precise, that n minus 2 is there. So that's the distribution of a correlation coefficient. We can use all of that information to calculate p-values and to calculate confidence intervals. So for large n, we're essentially on a normal curve. To do a hypothesis test, you'd simply be comparing your observed R. Your null value here is 0, so you're comparing your observed R to 0 divided by the standard error for R. R divided by its standard error gives you z-score, and you'd get an accompanying p-value. To build a confidence interval, you'd take the observed value of R in your sample, and you'd add or subtract the confidence limit is usually that z-value is going to be 1.96 for a 95% confidence interval, but if you wanted to make 99% or 90%, that z-value might change, times the standard error. And you'd be just plugging in here into the standard error the observed R, because we don't know the true R. That's for large n. For small n, you'd have to worry about the fact that you're on a t-curve. You might have to worry for really small n about the fact that it's an n minus 2 in the standard error. And again, you'd do a t, you'd be comparing R to its standard error to get a t statistic, or you'd be building a confidence interval, all in the same way that we've talked about already. What's kind of interesting about the correlation coefficient, if you look at those formulas that I just showed you, it turns out that whether or not a correlation coefficient comes out to be statistically significant depends on only two things: the magnitude of R that you observe in your sample and an n, the sample size. There's nothing else involved. So you can take the formulas that I just showed you and you can rearrange them a little bit, and you can show that there's a direct relationship between R and N. You can calculate the minimum size of the correlation coefficient that you would need to be statistically significant for every different sample size. And it's an approximation here, but you can take the formulas I had on the last slide, and basically to be statistically significant, the minimum R that's going to be statistically significant for a given sample size is roughly equal to 2 divided by the square root of n. It's a bit of approximation, but it works pretty well for almost all n. I can just plug in then, for example, to be statistically significant when you have a sample size of 10, 2 divided by the square root of 10 gives you that you're going to need to have a correlation of 0.63. It's going to need to be pretty big in order to come out statistically significant, and with only 10 to be confident that that's really different than 0. With 100, however, 2 divided by the square root of 100 gives you a value of 0.2. So you can have any correlation coefficient for any variables in your study that comes out to be 0.2 or greater when you have a sample size of 100 is going to be statistically significant. As you get to very big sample sizes, as I showed you before, say 1,000, 10,000, 100,000, the minimum correlation that's going to come out to be statistically significant, notice all of these when your sample size is 1,000 or greater, 0.06, 0.02, these are all less than 0.1 correlation. That would be considered essentially no correlation. It's so small that it's not meaningful, and especially when you get to like 0.006, 0.002, you can statistically distinguish those from 0, but they're so tiny that they are not clinically meaningful, as we talked about. So that's where that slide came from. I just want to mention, while we're talking about Pearson's correlation coefficients, just quickly, that if you have a small sample where you're violating the normality assumption, you'll want to use an alternative statistic to the Pearson's correlation coefficient called the Spearman rank correlation coefficient. And it's just like all the nonparametric tests we talked about last week. You're going to be ranking variables and building a correlation coefficient based on the ranks. So say you're looking at height and weight, you would rank everybody on height, you would rank everybody on weight, from the lowest to the highest height, the lowest to the highest weight. And then you look within a person, you look at the rank they got for height and the rank they got for weight, and you subtract those to come up with a difference in the ranks. And the Spearman rank correlation coefficient is built around the difference in those ranks. Obviously, if the differences in those ranks are extremely small, that would indicate that you're on a, those two variables were strongly related. If the differences in the ranks are very large, that would indicate that those two variables were not strongly related. But it's based on ranks, so you don't need to make any assumption about normality there.